All right, last lesson we were looking at how to name main group metals and nonmetals. We just simply took their names. We said that it was easy to look at how ions formed from what group number it was in. And the idea is that we filled the S and P to get that low potential energy. Now we're going to add a little bit of a twist, and that is with transition metals. We save those, remember, in your periodic table. Your transition metals are right in the middle. They are called your D block. And once again, the main idea is trying to get to a lower potential energy. And with transition metals, getting to a lower potential energy involves the electrons in those d orbitals, not just the S and P. So they form ions with a little bit different reasoning. Okay, let's look at just the electron configuration of iron, an example of a transition metal. And iron has 26, its atomic number, so we got 1s and 2s, 2p, 3s, 3p. Now this is where I said something takes a little bit different turn. Normally, remember the Bohr model of the atom? We said in n equals 1, we have the S. In n equals 2, we have S and P. In n equals 3, we have S and P and D. All right, well, in n equals 4, then, what happens is that as these orbitals start overlapping, the 4s actually comes in and dips in before the 3d. So your periodic table shows that. If you see on your periodic table where the d shows up, 1, 2, 3, it starts out in period 4, all right? So we got 4s, and then it goes to 3d. So your d's are always 1 behind whatever your period number is out here. So, in our electron configuration then, instead of going to 3d, we're going to go to 4s. Before we go to those 3ds, and see where iron is on your periodic table, you'll notice that it is 1, 2, 3, 4, 5, 6 into the d orbitals, and I'm going to show you how that plays out on the electron configuration. All right, so we're at 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, and the d orbitals, just like the p, are going to fill singly because that is lower potential energy. To fill those unfilled orbitals half, and then come back, all right? So that is what the electron configuration of a neutral iron atom looks like, okay? So what's going to happen is that when it forms an ion, it has more options, all right? For instance, it might just take out its valence electrons, which would be the 4s. Remember that the valence electrons are those in the outer energy level, and we look for the outer energy level, which has the biggest number. All right? So we might form an iron 2+ just by taking out and removing those 4s. All right? However, another option for iron, which would also give it a lower electron, a lower potential energy, is to take out one of the d's. Okay, so iron can form a +2 or a +3 ion. Because of that, this is the same for all transition metals. They will always form by first removing the s electrons, and then whatever logic there is to removing additional d, all right? And there isn't a specific guideline for this. It's unique for each transition metals. Trying to figure it out is difficult to do. But because iron can form more than one cation, we designate which one we're talking about with a Roman numeral. For instance, let me show you the formula of two compounds that are on your sheet. All right, we can't just say iron oxide like we did with main group metals, because we don't know if we're talking about iron 2 or iron 3. So what we have to do in naming is place a Roman numeral, and that Roman numeral is the charge, not the amount of iron. It is saying, okay, the iron 2 oxide, it is iron with a +2 forming a compound with oxide, which we already know. All right, in this one, it would be iron 3 oxide. Okay, and notice a very common mistake is just to put that number. And that is not what that Roman numeral means. The Roman numeral is saying this is the iron 3+, and it is forming a compound with oxide, which we know, main group nonmetal forms one ion. And then how we put them together is like that. Okay, so the difference then, if we have a transition metal in our compound, is in the name, we have to use a Roman numeral. So let's look at some of these examples on your paper. All right, and we have this formula. Okay, once again, I can't just say copper chloride. I first understand that copper is a transition metal. And then to know which copper I'm talking about, I have to see, well, how is it put together with that chloride ion, which I do know the charge of. So I look and I say, we're trying to figure out what that charge is, but we do know that chloride has a -1, it's a group 7 nonmetal, and we do know that there's 2 of them. So if I have a -2 and this is neutral, then this obviously has to be copper 2, doesn't it? So this is copper 2 chloride. All right, the rest of the naming convention is exactly the way it was with main group metal and nonmetal. All right? If they give you the name, it makes it a lot easier. For instance, cobalt 3 nitride. Well, that's telling me it's a cobalt +3. Nitride, I look on the periodic table, it is a group 5 nonmetal. So if I put these together to be neutral, the formula would simply be CON. All right? Okay, and let's do one more. Okay, once again, I identify that nickel is a transition metal. Because it's a transition metal, I can not just simply say nickel sulfide. I have to say which ion of nickel is it. And so I look and I see, well, I know sulfide is in group 6, so it has a -2. And it's in a 1-to-1 ratio with that sulfide, so that means this must be a nickel +2. So the name of this is nickel 2 sulfide. All right, so that is the twist on the previous lesson of a main group metal with a nonmetal. Now we have a transition metal with a nonmetal. Are there exceptions to this? Yes, unfortunately. All right, there are 2 exceptions. There are 2 transition metals that require no Roman numeral because of their nature, which we'll get into later, they only form one ion. Since they only form one type of ion, you don't need Roman numerals. And that is zinc only forms a +2, and silver only forms a +1. And you simply need to memorize those. Now, an easy trick is if you look at your periodic table that I have in your packet, you'll notice over here in group 3 is aluminum, all right? And since it's in group 3, we know it has to have a +3. Well, if you see where zinc and silver are in relationship to aluminum, it's kind of a stair step. So you could go 3, 2, 1, and that'll help you remember that zinc and silver are the two exceptions. They're the two transition metals where we do not need a Roman numeral. So in other words, the example on your sheet is this would simply be called silver chloride. You would not need to say silver 1 chloride, all right? Or if they just gave you this name, all right, zinc chloride, and then you freak out because it's transition metal and they didn't give you a Roman numeral, and that's where you have to remember what we said. Zinc is one of those exceptions where it only forms a +2. If it only forms a +2, then that has to be the formula. Okay, now those aren't the only exceptions. We got main group exceptions. There are 3 main group metals that require a Roman numeral. Yes, this just gets better. And that is lead, bismuth, and tin. All right, these 3, and they are called post-transition heavy metals because look at where they're at in the periodic table. All right, they're the only metals on the periodic table that are on the opposite side of d orbitals. Aluminum is way up here, okay? So aluminum is just a plain old main group metal. But tin, lead, and bismuth are post-transition heavy metals. And let's look at the electron configuration of tin to see how it forms ions, all right? And tin has 50 electrons, so this will take a minute. 1s, 2s, 2p, sorry. Okay, now notice how our D's are stuck right in between the S. We go to 4S, then we go back and finish the 3D, and then move into the 4Ps, okay? And so 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32. Oh, crap. Yeah. 33, 34, 35, 36, 37. 38, 39, 40, 41, 42, 43, 44, 45, 46, 47. 48, 49, 50. All right? Yes. No, actually, I think I should have stopped here. Okay, so on your periodic table, you see that tin is 2 into the 5p orbits, all right? And so tin will just, this is now the valence electrons in the outermost level. Okay, so tin is going to form a +2 by either taking out just the s orbitals, or it will take out the s and p and form a 4+. All right, so lead, bismuth, and tin are the 3 main group metals that require a Roman numeral because of the interference of these d orbitals. They act like more like transition metals and forming ions. All the other metals, as I said, aluminum, being on that side, don't have d orbitals to worry about. Okay, so just once again, so like if you had tin then in a compound, you would have to say tin 2 chloride, not just tin chloride. All right, so just a summary of what we just learned. With transition metals, because they can form more than one type of ion, we are required to put in Roman numerals. Main group metals, S and P, because they have a different dynamic going on with establishing low potential energy, only form one type of ion. And there are exceptions to this. The exceptions for the transition metals that do not require Roman numerals are zinc and silver. And the exception for the main group metals that do require Roman numerals are lead, bismuth, and tin. All right, now that you're totally confused, we'll stop.